The compute dollar versus the Token-Yuan, the global race to price, financialize, and settle industrial cognition. Summary statement. The next monetary order may not be determined by who builds the smartest AI, but by who defines, prices, financializes, and settles the world's industrial cognition. Section 1. Introduction. A new monetary contest. The race to build artificial intelligence is often portrayed as a competition between increasingly capable language models, faster computer chips, and larger data centers. While these technological advances are undeniably important, they may not represent the true strategic prize. The deeper contest is economic. History suggests that civilizations do not merely compete to produce valuable resources. They compete to establish the financial architecture through which those resources are measured, traded, financed, and settled. The dominant monetary systems of history have typically emerged alongside the dominant productive technologies of their age. During the industrial era, oil became the indispensable fuel of economic production. Nations required petroleum to power transportation, manufacturing, logistics, agriculture, and military capability. As oil markets matured, they developed standardized units of measurement, benchmark pricing, futures markets, and ultimately a settlement architecture that became overwhelmingly centered on the United States dollar. The petrodollar was therefore not simply about oil. It represented the convergence of a critical industrial resource with a dominant financial ecosystem. Artificial intelligence may be initiating a similar transition. The essential resource of the emerging machine economy is no longer hydrocarbons. It is industrial cognition. Industrial cognition refers to intelligence that can be produced, replicated, distributed, purchased, and deployed at industrial scale. It transforms electricity, semiconductors, networking infrastructure, algorithms, and data into economically useful cognitive capability. Just as electricity transformed physical energy into productive work, industrial cognition transforms compute into productive intelligence. This distinction is important. The discussion surrounding artificial intelligence often focuses on the capabilities of individual models. However, history suggests that lasting economic power rarely resides solely in the end product. Instead, it accrues to those who establish the standards, infrastructure, and financial mechanisms through which entire industries operate. The question therefore shifts dramatically. The strategic competition is no longer simply who builds the smartest AI. Instead, it becomes who defines the economic architecture through which machine intelligence is measured, traded, financed, and settled. From data to compute. Only a few years ago, one of the defining phrases of the digital economy was, "Data is the new oil." The analogy captured an important truth. Human activity continuously generated vast quantities of digital exhaust. Search queries, purchases, social interactions, location histories, and browsing behavior became the raw material from which technology companies extracted value. Data itself held relatively little value until refined through machine learning, statistical modeling, and behavioral analysis. The process resembled an industrial refinery. Raw human behavior entered one end of the system. Predictive intelligence emerged from the other. That intelligence was then sold to advertisers seeking to influence consumer decisions, optimize marketing expenditure, and improve customer acquisition. The true product was never data itself. It was prediction. The emerging AI economy follows a similar pattern, but the underlying resource has fundamentally changed. Today, the scarce industrial input is increasingly compute. Graphics processors, specialized AI accelerators, networking infrastructure, memory bandwidth, and electricity collectively produce something far more valuable than raw computational cycles. They produce usable intelligence. This represents an important conceptual shift. The internet economy primarily monetized human attention. The AI economy increasingly monetizes machine capability. Instead of extracting value from human behavioral data alone, compute transforms physical infrastructure into autonomous reasoning, planning, perception, and execution. Intelligence itself becomes an industrial output. The evolution can therefore be summarized as follows. Data economy, humans produce behavior. Platforms refine behavior into prediction. Advertisers purchase influence. Human behavior becomes the raw fuel. Compute economy infrastructure produces industrial cognition. Models transform compute into autonomous capability. Machine intelligence becomes productive labor. Industrial cognition becomes the new fuel. This transition extends beyond software. As autonomous agents, robotics, and synthetic labor and automated manpower (SLM) mature, machine intelligence will increasingly perform economically productive work on behalf of humans. Compute ceases to be merely a technical resource and instead becomes the operational fuel that powers synthetic workers. The implications extend far beyond artificial intelligence itself. They reach into capital markets, monetary systems, geopolitical competition, and the future architecture of the global economy. In the sections that follow, we examine how this emerging resource may evolve through the familiar stages of commodity development: measurement, standardization, price discovery, financialization, and settlement, and why the United States and China appear to be pursuing two fundamentally different strategies for capturing that future. Section 2. Industrial cognition as a commodity. Every major industrial commodity follows a remarkably consistent path before it becomes indispensable to the global economy. First, it must be measurable. Second, it must become standardized. Third, markets establish mechanisms for price discovery. Fourth, financial institutions develop instruments to hedge, finance, and trade it. Only then does it mature into a globally recognized economic asset. Oil followed this progression. Electricity followed this progression. Natural gas, agricultural products, metals, shipping containers, and even internet bandwidth all underwent similar transitions. Artificial intelligence now appears to be entering the same evolutionary process. The critical insight is that markets cannot efficiently allocate a resource until they can first measure it. Historically, measurement precedes markets. A barrel standardized oil, a kilowatt-hour standardized electricity, a container standardized global shipping. The emerging AI economy now faces the same challenge. What is the equivalent standardized unit for industrial cognition? This question may ultimately prove more important than the race to build the most capable model. The measurement problem. Today's AI ecosystem remains fragmented. Different frontier models exhibit different capabilities. Different hardware architectures deliver different performance. Different inference engines optimize for different workloads. Raw token counts, GPU hours, or floating point operations are engineering metrics, but they are poor economic measures because they fail to capture the quality of the intelligence being produced. 1 million tokens generated by one model may represent dramatically different cognitive value than 1 million tokens generated by another. Similarly, identical GPU hours can produce vastly different outputs depending upon software optimization, model architecture, and hardware efficiency. Without standardization, meaningful price discovery becomes difficult. Markets therefore require a benchmark. One promising proposal is the Standard Inference Token (SIT). Rather than treating every generated token as equivalent, the SIT represents a benchmark-adjusted unit of inference output that incorporates capability thresholds and standardized evaluation metrics. Conceptually, SIT performs for industrial cognition what the barrel performs for oil. It provides a common language through which heterogeneous systems become economically comparable. The importance of this distinction cannot be overstated. The standard inference token is not a currency. It is a unit of measurement. Just as oil can be priced in barrels while settling in multiple currencies, industrial cognition can be measured in SITs regardless of whether settlement ultimately occurs in dollars, renminbi, stablecoins, or other monetary systems. Separating these concepts dramatically clarifies the discussion. Measurement and settlement are distinct economic functions. From measurement to financialization. Once industrial cognition becomes measurable, the next stage naturally follows. Markets emerge. Price discovery begins. Financial instruments develop. This transition has already started. The United States has largely approached the problem from the infrastructure side. Its financial innovation has focused on pricing the machinery that produces intelligence. GPU rental markets, compute indices, and emerging futures contracts attempt to transform physical AI infrastructure into tradable financial assets. In effect, the United States is pricing the machine. China appears to be exploring a different direction. Rather than emphasizing the hardware itself, its emerging discussions have focused on standardizing and pricing the output produced by that hardware. Instead of asking, how valuable is a GPU hour? The question becomes, How valuable is a standardized unit of industrial cognition? This distinction reflects two fundamentally different philosophies. The American approach begins upstream, financialize the infrastructure. The Chinese approach begins downstream, financialize the utility produced by that infrastructure. Both approaches ultimately seek the same objective. They seek to transform artificial intelligence from a technological capability into a mature commodity market. Two competing paths. Viewed through this lens, the strategic divergence becomes much clearer. The United States currently possesses substantial advantages in frontier semiconductor design, proprietary AI models, hyperscale cloud infrastructure, and the deepest capital markets in the world. Financializing GPU capacity naturally complements these strengths. China's comparative advantages are different. Its strategy increasingly emphasizes abundant electricity generation, manufacturing scale, embodied AI, open-weight frontier models, and cost-efficient deployment. Pricing industrial cognition itself aligns more naturally with these strengths. The contrast can be summarized simply. United States prices the machinery that produces cognition. China prices the cognition produced by the machinery. Neither approach is inherently superior. Each reflects the comparative advantages of its respective ecosystem. More importantly, they reveal that the emerging contest extends well beyond artificial intelligence itself. It has become a competition over how industrial cognition will ultimately be measured, benchmarked, traded, and valued. That competition may prove just as consequential as the race to build increasingly capable AI systems. Because once a resource becomes measurable and financially tradable, the next question inevitably follows. Which monetary system will become the preferred settlement layer for that resource? That question moves us from metrology into monetary architecture, the subject of the next section. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Section 3. From financialization to monetary architecture. Once a commodity becomes measurable and financially tradable, the final stage of its evolution concerns settlement. This distinction is subtle but fundamental. Measurement determines what is being traded. Financialization determines how it is priced, hedged, financed, and exchanged. Settlement determines which monetary system ultimately clears those transactions. These are separate layers. Conflating them obscures the true strategic competition. A barrel of oil is a unit of measurement. West Texas Intermediate WTI is a financial benchmark. Neither dictates the currency in which a transaction must settle. The petrodollar emerged not because oil naturally required dollars, but because geopolitical agreements, financial infrastructure, market liquidity, and international trust collectively reinforced the United States dollar as the preferred settlement currency. The same distinction applies to industrial cognition. If the standard inference token, SIT, or some future equivalent, becomes the accepted benchmark for machine intelligence, that alone does not determine whether transactions settle in US dollars, Chinese renminbi, stablecoins, or another monetary system. The benchmark solves the measurement problem. It does not automatically solve the settlement problem. This observation dramatically changes the strategic landscape. The contest is no longer simply about building better models or cheaper compute. It becomes a contest over the financial architecture that surrounds industrial cognition. The four competitive layers. Viewed through this framework, the emerging AI economy consists of four distinct but interconnected competitions. Layer 1. Production. Who produces industrial cognition? This layer encompasses electricity generation, semiconductor manufacturing, data centers, networking infrastructure, and frontier AI models. It represents the physical foundation of the machine economy. Without this infrastructure, industrial cognition cannot exist. Layer 2, metrology. How is industrial cognition measured? This is the role of standardized benchmarks such as the proposed standard inference token. Measurement creates comparability. Comparability enables markets. Without standardized units, meaningful price discovery remains impossible. Layer 3, financialization. How is industrial cognition priced, financed, hedged, and traded? Here we encounter futures markets, options, derivatives, benchmark indices, and compute exchanges. This layer transforms industrial cognition into an investable and hedgeable economic asset. It is the bridge between technology and capital markets. Layer 4, settlement. Which monetary system clears the trade? This layer ultimately determines where structural monetary demand accumulates. Will industrial cognition settle primarily through dollar-denominated financial markets? Will alternative systems emerge around the renminbi or the ECNY? Will privately issued stablecoins become the preferred settlement rail for autonomous machine-to-machine commerce? The answer remains uncertain, but the question itself may define the monetary politics of the coming decades. The compute dollar and the token yuan. This layered perspective also clarifies the different strategic trajectories currently emerging. The United States appears to be pursuing an upstream strategy. Its comparative strengths lie in frontier semiconductors, proprietary AI models, hyperscale cloud infrastructure, mature financial markets, and global dollar liquidity. Financializing compute infrastructure naturally reinforces these existing advantages. GPU rental markets, compute futures, and infrastructure financing all strengthen demand for the ecosystem that produces industrial cognition. China appears to be pursuing a downstream strategy. Rather than emphasizing hardware scarcity, its competitive advantages increasingly derive from abundant electricity, manufacturing scale, open-weight frontier models, embodied AI, robotics, and low-cost inference. Its emerging focus on standardized inference output reflects this orientation. One strategy prices the machine, the other prices the work produced by the machine. These are not merely different financial products. They represent two different philosophies regarding where enduring economic value ultimately resides. One emphasizes ownership of scarce infrastructure. The other emphasizes ownership of abundant utility. The machine economy. The significance of these competing architectures becomes even more profound once autonomous agents enter the picture. Today's cloud infrastructure remains overwhelmingly human-directed. Businesses purchase compute. Engineers provision infrastructure. Executives allocate budgets. Artificial intelligence assists decision-making, but rarely controls capital allocation itself. This arrangement is unlikely to persist indefinitely. The more transformative milestone occurs when humans cease specifying every infrastructure decision and instead delegate operational authority to intelligent systems. Initially, this delegation may be narrow. Humans define objectives. Machines optimize execution. Over time, however, the scope of delegation expands. Machines begin determining what compute they require, where it should be acquired, when demand should be shifted geographically, how redundancy should be managed, which models maximize capability per unit cost. Eventually, autonomous systems begin procuring infrastructure directly within predefined operational constraints. This transition fundamentally changes the character of demand. Instead of humans purchasing compute on behalf of machines, machines increasingly purchase compute on behalf of themselves. Demand becomes recursive. Machine intelligence performs economically productive work. That work generates revenue. Revenue funds additional compute. Additional compute expands capability. Capability generates additional economic output. A self-reinforcing economic loop begins to emerge. At that point, industrial cognition ceases to resemble traditional enterprise software. It begins resembling a new class of productive capital. The implications extend far beyond artificial intelligence. They reach directly into monetary economics. Because whichever ecosystem ultimately becomes the preferred marketplace for allocating, financing, and settling this recursive demand may also become the monetary foundation upon which autonomous machine economies increasingly operate. Section 4. The next monetary order. The discussion surrounding artificial intelligence often focuses on who will build the most capable model, train the largest neural network, or deploy the most advanced robotics. Those questions are undoubtedly important. History, however, suggests that technological leadership alone rarely determines long-term economic power. Civilizations achieve enduring influence by constructing the financial architecture that surrounds transformative technologies. Railways required standardized gauges. Electricity required standardized measurement. Containerization required standardized shipping units. Financial markets emerged only after these standards became widely accepted. Artificial intelligence now appears to be approaching the same inflection point. The race is no longer confined to algorithms. It increasingly concerns the institutions that will govern industrial cognition itself. Who will define the benchmark? Who will establish the reference price? Who will create the derivatives? Who will finance the infrastructure? Who will provide the liquidity? Who will settle the transactions? These questions may ultimately prove more consequential than benchmark scores or parameter counts. From human economies to machine economies. Perhaps the most profound transition discussed throughout this paper concerns the evolution of economic agency. For centuries, markets have largely existed to coordinate human decisions. Humans earned income, humans consumed goods, humans allocated capital. Artificial intelligence initially entered this system as a tool. It enhanced productivity while humans remained firmly in control of purchasing decisions. That relationship is beginning to change. As agentic AI matures and synthetic labor and automated manpower, SLAM expands into logistics, manufacturing, transportation, healthcare, finance, and countless other sectors, intelligent systems will increasingly become participants rather than merely instruments. The progression may unfold gradually. Humans purchase compute, machines execute tasks, humans define objectives, machines optimize procurement, machines provision infrastructure, machines transact with other machines. Eventually, autonomous systems may negotiate directly with compute providers, energy markets, logistics networks, financial exchanges, and other digital services in pursuit of predefined economic objectives. This is not merely automation. It is the emergence of machine-directed economic coordination. When millions, or perhaps billions, of autonomous agents begin continuously purchasing compute, storage, bandwidth, robotic services, and industrial cognition, demand itself changes character. It becomes continuous rather than episodic, recursive rather than manually budgeted, machine-paced rather than human-paced. The economic consequences of this transition may prove as significant as the industrial revolutions that mechanized physical labor. The 21st century may instead be remembered for industrializing cognition. An open strategic contest. None of the outcomes described in this paper are predetermined. The United States may successfully reinforce dollar dominance by financializing compute infrastructure through its semiconductor ecosystem, hyperscale cloud providers, and capital markets. China may successfully establish globally accepted standards around inference output while leveraging abundant electricity, manufacturing capacity, embodied AI, and alternative settlement infrastructure. A third possibility also exists. Rather than converging upon a single global architecture, the world may develop multiple competing ecosystems with varying degrees of interoperability. Industrial cognition could be measured using common benchmarks while settling through multiple monetary systems. Regional standards could coexist. Capital markets could fragment. Autonomous agents could dynamically optimize across competing infrastructures. History rarely produces perfectly uniform outcomes. Nevertheless, regardless of which geopolitical architecture ultimately prevails, the underlying direction appears increasingly clear. Industrial cognition is evolving into a measurable, tradable, financeable economic resource. Markets are beginning to construct the institutions necessary to allocate it. Financial systems are beginning to compete for the right to price, finance, and settle industrial cognition. And autonomous agents may eventually become the largest participants within those markets. Section 5. Conclusion. The transition from the data economy to the compute economy represents more than another technological cycle. It represents the emergence of a new industrial resource. Just as oil powered the factories, transportation networks, and mechanized labor of the 20th century, industrial cognition may power the autonomous systems, synthetic labor, and machine economies of the 21st. The strategic contest therefore extends beyond artificial intelligence itself. It encompasses production, measurement, financialization, settlement. Each layer represents an independent source of economic leverage. Each layer may produce different winners. The nations that succeed will not necessarily be those that build the smartest models. They may instead be those that establish the standards, financial markets, and monetary infrastructure through which industrial cognition is measured, priced, financed, and settled. Ultimately, the competition between the compute dollar and the token yuan is not simply a contest between two currencies. It is a contest between two competing visions of how the world's future machine economy will be organized. One seeks to financialize the infrastructure that produces intelligence. The other seeks to financialize the intelligence produced by that infrastructure. Whichever architecture ultimately achieves the broadest global adoption may influence not only the economics of artificial intelligence, but also the monetary foundations upon which autonomous civilization increasingly operates. The next monetary order may not be determined by who builds the smartest AI. It may be determined by who defines, prices, financializes, and settles the world's industrial cognition.